Hello and welcome to this next tutorial. Now, so far we have looked at how a sequence of text comes into the model, is tokenized, the embedding values are retrieved, and how the positional information is injected. We've then gone on quite an adventure looking at the engine of the transformer, the self-attention block. Now we're going to move on to the final part of this architecture. Now, for inference or prediction, the model really only cares about the final token in the sequence. By this stage, as we've seen over the past couple of videos, that tokens vector has already absorbed information from all of the others through attention, so it's context rich and it's ready to represent what comes next. So in our example, we would take the final vector for the token corporate, which in our simplified case is a vector with just 3 values in it. In the real world, in a GPT type model, this would of course be much bigger. Either way, let's think about our end goal here. We want to know from all of the tokens in our set token vocabulary, which one is most likely to come next in the sequence. She packed her bags for the corporate. And to do this, we would need some sort of probability for each of those possible tokens. At this stage, however, we just have this vector of 3 numbers, so we essentially need to project this vector up to the size of the model's full vocabulary. And this is what the linear layer does. For a GPT type model, this vocabulary might be around 50,000 tokens, but for our example, we're just going to use 6 tokens. And you can see those in grey boxes there, so conference, meeting, event, holiday, banana, and dog. Now, this is only for illustrative purposes, of course. Remember, our sequence, she packed her bags for the corporate, contains other tokens. They would be in the full vocabulary, of course. We're just ignoring them for our example here. So the linear transformation that takes place utilizes a set of weights and a bias value. And again, these are values that are learned and refined during the training process. Now, because our vector size is 3 and because our vocabulary size is 6, you can see that our linear weights matrix at the top right matches these dimensions, so 3 by 6. And underneath that, we have a bias value for each vocabulary token, so a size of 6. Again, as we've become so accustomed to, it is matrix multiplication, so these values all multiplied, then summed, and after those have been summed, the bias value is added, giving the raw output score for that first possible next token. It would be the exact same process for the next token, multiplying the relevant values, adding them up, then adding the bias value on top to get the score for the next token. And this process would continue until we have all our raw output scores for each token in the vocabulary. And that is the linear projection done. But as we know, what we want is not these raw values. We want them represented as probabilities, and this is exactly what our softmax function will give us again. Before we do that, as we have some positives and some negatives, we want to exponentiate them just like we did earlier when dealing with our attention scores. Now, in that prior process, to combat any excessively small or large numbers, we also applied scaling first, but that isn't a risk here, so we don't need that step. Anyway, you can see those exponentiated numbers on screen here, so remember that is Euler's number to the power of our raw score for each of these. But this means that we are one step away from the end of this journey. If we apply the softmax function to these, so essentially we add all of the values up, then divide each of the individual values by that total, we will get these final values, and these are the model's predicted probabilities for each token being next in our sequence. So where we had she packed her bags for the corporate, the model calculated these probabilities for all tokens in our vocabulary. And if we simply take the highest or most likely, our sequence is predicted to be she packed her bags for the corporate conference. How cool is that? Now, in reality, the model won't always just take the token with the highest probability. That approach is called greedy sampling, but there are other approaches too. Often the next token will be picked from the probability distribution itself. So here there would be a 43% chance that conference was selected as the next token, a 28% chance for meeting, a 21% chance for event, and so on. And often this is done with a cap on probability, so nothing could be selected with a probability less than 20%, for example, just to ensure nothing too crazy is selected. You'll often hear about the temperature setting for prediction too, and this can be adjusted based on whether you want your selections to be more reliable or more creative. So there we go, that is an overview of how this model takes the context-enriched vectors, projects that information up to the full vocabulary, and then creates some probabilistic values for each possible next token. In the next tutorial, what I want us to do is run through this full process from end to end at a really high level. I think this will be nice to do as we have gone very deep into some heavy concepts over the past few videos. It will be really useful to see all of this in one run through. I also want to run through a few caveats and considerations about what we've covered over the past couple of videos. I'm looking forward to this one. I think it's going to be really valuable, so I will see you there.